Hi everyone. In this video, we will continue our discussion of measurable functions by looking at some important properties of measurable functions that we will need when we begin to define the Lebesgue integral, which we will do in the next video. So to begin, anytime in both Math 5610 and Math 5620, anytime we've defined sort of a property X that a function has, one of the immediate sort of things we do is ask, well, is that property preserved under multiplication, addition, a subtraction, multiplication by a scalar, all these sorts of different things. And we've had these sort of algebra of X functions for many different kinds of X, right? So we have an algebra of continuous functions, algebra of differentiable functions, right? And so we might ask ourselves, can we get an algebra of measurable functions? And the answer, unsurprisingly, is yes. So if we let f and g be measurable functions on a common domain, so remember, f and g being measurable functions means they satisfy one of those measurability conditions and they have a measurable domain. And in this case, they have a measurable common domain. So they're both defined on the same set. And let c just be some constant. Then the function f plus a constant c, c times f, f plus or minus g, f squared, f times g, all of these are measurable functions. Now, of course, if you just proved f plus g, a constant times f, and f times g, you would get all the rest of these. So this is not meant to be like some minimal sort of proof, but this is just to give you a general theorem that explains that all of these different functions are measurable. Now, I'm not going to prove every one of these, but I'll sort of sketch out a couple of them just so you get sort of the idea and the spirit of how these work. Okay, so to begin, you can imagine, let's say we want to prove that c times f is measurable. Okay, well then what do we need to do? We need to show that one of the measurability conditions is satisfied. So say I wanted to show that the set of all x in the domain such that c times f of x is less than r. I want to show that's a measurable set. Okay, but I know that f is measurable. So what I'm going to do is I'm going to break this out into a couple of different cases. Okay, I'm going to break this out into the case that c is positive, that c is negative, and that c is 0. Okay, so if c is positive, then this set is equal to the set of all x in D such that f of x is less than r divided by c. Right? So if c is positive, I can divide both sides of this inequality by c. So these are exactly the same set because these are entirely equivalent conditions. And I know that this set is measurable because f is measurable. So this set is measurable from the measurability of f, right? Any set of the form, set of all x and d such that f of x is less than some number is measurable. That's what it means for f to be measurable. But that's equal to this set, and this is a measurability condition for c times f, so c times f is measurable. If c is less than 0, I can still divide both sides here by c, but my inequality is going to flip. But that's okay because one of my other measurability conditions for f, right, is that the set of all x such that f of x is greater than any number is also measurable. So here, this set is measurable, again, from the measurability of f, but this is equal to this set, okay? And this is a measurability condition for c times f. If c is equal to 0, then what is this? Then this is the set of all x in D such that 0 is less than r. Well, this set, this condition here doesn't depend on x, right? So if R is positive, then you just get back the whole set D, right? The set of all X such that 0 is less than R. If R is positive, well, that's just all of D. It's the empty set if R is less than or equal to D. But because F and G are measurable, we're assuming, or sorry, because F is measurable, we're assuming its domain is measurable. The empty set is always measurable. So these are all measurable. So again, here, you just break it out into cases, right? But in any case, you get that this set is measurable, and therefore C times F is measurable. All right. Just to give you one other idea, what if you wanted to prove that F plus G is measurable? Now, in this case, we need to be a little more careful. Okay. So what I would want to establish here is I really want to look at the set of all X in my domain such that F of X plus G of X is less than R. And I want to prove that that is measurable. Well, what I'm going to claim, and I'll explain why this is true in a second, is I'm going to claim that this set can be written as the union over all rational numbers P of sets of the form X and D such that F of X is less than P, intersect X and D such that G of X is less than R minus P. All right. So here's fundamentally the idea. For a particular, so to show this inequality, or sorry, to show this set equality, I need to show that the left set is a subset of the right set, and the right set is a subset of the left set. Okay. So how can I think about doing this? Well, certainly, if I take something on the right-hand side, okay, if I take an X value that's in this union, well, if it's in the union, then it has to be in one of the pieces. Okay, so if it's in one of these sets, each of these sets is an intersection, then for some p-value, it is in both of these sets. So for some p-value, I wanted to change colors. So for some p-value, you would have both that F of X is less than P and G of X is less than R minus P. But if you just add those inequalities together, you get F of X plus G of X is less than R minus P plus P, which is just R. So for any X value that lives over here, it's also true that F of X plus G of X will be less than R, so it lives over here. All right. Now, what about going the other way? Okay. So what if I take an X such that F of X plus G of X is less than R? Well, if F of X plus G of X is less than R, that implies that F of X is strictly less than R minus G of X. Okay. I can then find, so this implies that there exists some rational number P that lives between F of X and R minus G of X. Okay. So if my X is such that F of X plus G of X is less than R, then there is some rational number such that F of X is less than P and P is less than R minus G of X. Said another way, G of X is less than R minus P. So if I live in this set of X values such that F of X plus G of X is less than R, then for some rational number Q, I live in one of these sets. Therefore, I must be in the union of all of them. All right. So I do this sort of set theory argument. Why does this help me? Well, F is measurable. So this set is measurable because of F is measurable. Right? This is just one of the sets from a measurability condition for F. This set is measurable because G is measurable. And then I have an intersection of measurable sets, which is measurable. And then I have a countable union of those measurable sets. And a countable union of measurable sets is measurable. Therefore, this set must be measurable. Okay. So again, we didn't work through all of them, but what I want you to sort of take away from this is that the way these sort of measurability arguments often go is you have a set you need to show is measurable in order to show that your function is measurable. You need to use some set theory to help you understand an alternate way of writing that set. In the first example here, it was really just playing around with some inequalities, right? In the second case, we actually needed to do a little more sophisticated set theory to re-express this set as an appropriate intersection or union or whatever of measurable sets so that we could then apply the fact that measurable sets are a sigma algebra to get measurability of this set. All right. So, that's fine. I mean, I don't think these arguments, again, these arguments are in many ways, the hard part is not the analysis, it's the set theory. Once you do the set theory, right, there's almost nothing to be done other than to say, oh yeah, the set of measurable sets is closed under unions, intersections, all of those things. So they're only bad because the set theory can be a little complicated, right? And so here, and I'm not trying to, set theory is certainly an important part of analysis. But again, here, the difficulty is often figuring out how to appropriately express it in a set theory way that makes the analysis portion of it fairly trivial. I should say that this is a fairly common thing in analysis. In fact, you can often take advantage of either set theory or topology or some other sort of area of math to almost trivialize the analysis part of it. If you sort of, and this happens even outside of analysis, right? It's sort of like if I take the right lens on this problem or looking at it from the right perspective, then what I need to do is trivial, right? However, figuring out that right lens could be very difficult, right? And often there's a trade-off too. So maybe you don't want to do that much topology or set theory, but so that means the analysis is a little bit harder, right? It's a trade-off we make in solving problems. All right, so we've seen then that the sum of measurable functions, difference of measurable functions, those all give us back measurable functions. I might ask myself, so what if I have a sequence of measurable functions all on a common domain? Well, it actually turns out that if I take, say, the supremum of the first k of those functions, that's going to give me back another function, and that function will be measurable. In fact, if I take the supremum over the infinite set of functions, right, the infinite sequence of functions, that will give me back a measurable function. Similarly, for infimums, right? If I take the infimum of the first k functions in the sequence, I will get a measurable functions. And even if I take the infimum over all the infinite collection of functions in that sequence, I will also get back a measurable function. Now, again, let's see how this works. The spirit of these proofs is going to be similar to what we were just discussing. All right. So let's start with we're just going to do this for the supremum cases. The infimum cases are almost identical. You just flip some inequalities. All right. So let's give a name to, so let me let F be the supremum of F1, F2, up to Fk. And here we're writing supremum, but you can really think of this as a maximum, right? A supremum over a finite set is just going to be the maximum of each of these. So, right, really what I'm doing here, right, if I want to know what f of x is for some particular x, I plug that x into each of my k functions, and I take whichever one gives me the biggest value. That's going to be the value of f of x. All right. So I want to show that this is measurable. Okay. Then for any r, any real number r, let me look at the set. I'm going to look at the set of all x, set of all x in my domain, such that f of x, I think here it's going to be a little easier to deal with. F of x is greater than r. And what I claim, again, I need to do some set theory here. I want to express this in a different way, right? And so I claim that this is equal to the union over all natural numbers k. Oh, sorry, not over all natural numbers k. I'm getting ahead of myself. This is the union, sorry, for n equals 1 to k of set of all x such that f sub n of x is greater than r. All right. So here's the idea. We have to ask yourself, why is this true? We will need to show this set equality. Okay, let's think through it. So what if I take something that's in the left-hand set? I need to show that it's also in the right-hand set. So if I take an x value such that f of x is greater than r, well, what was f of x? F of x was the maximum of f1 of x, f2 of x, f3 of x, all the way up to fk of x. Okay. So if f of x is greater than r, then that means that f sub n of x must be greater than r for every r. Okay. So certainly if I take something in this set, then f sub n of x is going to be greater than r for all of these. Okay. Because f of x is the supremum of all of these things. All right, now let's go the other way. What if I take something over here in this union? Okay. If I take something over here in this union, then it's in one of these. So let's say that f sub I of x, right, if I'm in the union, then that means f sub I of x is greater than r. Well, if f sub I of x is greater than r, then certainly the supremum over all functions f, that must be greater than or equal to this particular one. Okay. So if for some particular I value between 1 and k, f sub I of x is greater than r, then f of x, which is the supremum of f sub n of x over all n between 1 and k, must be less than f of x, and they're both must be greater than r. Okay, so something over here in this union is in one of these particular sets. If it's in one of these particular sets, then it must be in this set. Okay, so now how does that help us? Well, now this set that I want to know if it's measurable, I know that each of my f sub n's are measurable. So this set then is just a finite union of measurable sets, which is measurable. Okay, so this is a finite union of measurable sets, and hence measurable. All right. Now, what if we change this, right? So this proves that if I take a supremum over a finite number of these functions, then I will get another measurable function. But what if I take the supremum over all of them? So now I can imagine what would change if instead I looked at G being the supremum over all natural numbers of f sub n. Okay. Well, it turns out almost nothing changes in the proof. Here, instead of going from 1 up to k, I'm just going to go from 1 up to infinity. Okay. Now, again, I have to be a little careful here because this is now like as I think about it, this is now really a supremum. It's no longer a maximum, right? So when I take a supremum over an infinite set, right, there may be no maximum value, right? It could be that it's just a supremum here. It's an upper bound, but it's just a least upper bound. But nevertheless, the same argument works to show this equality, the set equality. If x is such that f of x is greater than r, well, f of x is an upper bound for the set of all fn's. So actually, fn of x must be greater than r for every for every n. So if x is such that f of x is greater than r, it's in every set of this form. So it's certainly in the union. If I take a particular one, then f sub I of x is greater than r, then f of x must still be greater than r. Same argument as before. Sorry, except I guess now we should call these, this is g, right? But again, it's just, you just change the k to infinity. And now you get that this set, it's no longer a finite union, but it's a countable union of measurable sets, and hence it's measurable. Okay. Again, in femums, these work almost exactly the same way, but just flip the inequalities, and that will make your life perfectly easy. And it's essentially the same arguments. Again, you just flip these because now you're dealing with infemums, but things go more or less the same. Again, I sort of like things like this because I can show you the proof in one direction. And if you're feeling a little unsure, go try to write out the proof for the infemums. And if you have questions, email me. We can see, if you're really understanding it, or maybe if there's still some gaps in your understanding that we can help fill. All right. Now, one of the last sort of pieces we want to deal with here, again, we're sort of, this last little bit is dealing with sequences of measurable functions. And I actually want to go back and think about what do we even mean when we talk about a sequence of functions? What do we even mean by convergence? So if you will recall back in Math 5610, we looked at two different types of convergence of sequences of functions. We looked at uniform convergence of a sequence of functions, and we looked at pointwise convergence of sequences of functions. Now, one of the things we saw was that uniform convergence implies pointwise convergence, but not vice versa, right? And now here we want to add a new type of convergence. This is going to be called convergence almost everywhere. It's sometimes called pointwise almost everywhere convergence. And so we're going to say that a sequence of functions fn converges to f almost everywhere if and only if the set of values for which f sub n does not converge to f has measure 0. And in that case, we'll write f sub n converges to f, and then we'll put this a dot e here, standing for almost everywhere. Okay. Now, what I want you to recognize here is that really what we're doing is we're now defining an even weaker type of convergence called convergence almost everywhere. Note that it doesn't even really require a proof. If you have a sequence of functions that converges pointwise, then f sub n does not converge to f on the empty set, right? If f sub n converges pointwise to f, then f sub n converges to f everywhere. So the set on which it does not converge is the empty set, which has measure 0. So if they converge pointwise, they certainly converge almost everywhere. But as we'll see here momentarily, there are sequences of functions that converge almost everywhere, but do not converge pointwise. Now, a sort of trivial way to do this, and in fact, the way we'll sort of see, is you just take it to you take some pointwise convergent sequence of functions, and you take some point or measure zero set of points and make it not converge on that set. So let's actually see a particular example of this. So let's consider the sequence of functions f sub n defined on the interval 0, 1 into R by f sub n of x is equal to n if x is rational, and 1 over n otherwise, or said another way, if x is irrational, right? Then we're going to claim that f sub n converges to 0 almost everywhere on 0, 1. However, it does not converge pointwise on 0, 1. Now, we can sort of deal with that right off the bat. How do I know that f sub n does not converge to 0 everywhere? Well, if I look at on the set of rational numbers, right, what's happening, this function is going 1, 2, 3, 4, 5, like it's diverging, right, on the rationals, right? On the irrationals, however, it's converging, right? As n goes to infinity, this is going to 0, okay? So the first thing I want to note here is on the Q complement intersect 0, 1, okay? So just make sure we're clear on what this is, right? This is the irrationals in 0, 1, okay? So on Q complement intersect 0, 1, f sub n of x is just equal to 1 over n, right? For irrationals between 0 and 1, f sub n of x is just equal to 1 over n. And so the limit as n goes to infinity of f sub n of x is equal to 1 is equal to the limit as n goes to infinity of 1 over n, which is simply 0. So on the irrationals between 0 and 1, this is converging pointwise to 0. On the rationals between 0 and 1, f sub n of x is equal to n, which diverges. So what can we conclude from all of this? Hence, f sub n does not converge to 0 on 0, 1, but does converge to 0 almost everywhere on 0, 1, since, so remember, what does it mean to converge almost everywhere? It means the set where it doesn't converge has measure 0. So since the measure of, this is where it doesn't converge, Q intersect 0, 1, this has measure 0. Why? Q is countable, and we've shown that every countable set has measure 0. Okay. So this does not converge pointwise, but it does converge pointwise almost everywhere on 0, 1, because the set where it doesn't converge, it has measure 0. So essentially what we're doing, we're defining this weaker type of convergence, which is essentially to say, well, it doesn't converge everywhere, but the places that it doesn't converge, they're small, right? And they're small in the sense of Lebesgue measure, right? So again, this is just an alternate way of talking about convergence. Now, a reasonable question to ask is, I mean, okay, we could do this, but why? It turns out that measure 0 sets, we'll see that they are actually sets that in terms of the Lebesgue integral we're going to define, they will be negligible. So these are sort of like, you know, when you're dealing with Riemann integration, you don't worry about changing some, say, the value of a function at some finite set of values. That won't change the value of an integral. Well, it turns out for Lebesgue integration, as we'll see, that changing the values of the function on a set of measure 0 will not change the value of the Lebesgue integral. So here, we're sort of okay if things go wrong on a set of measure 0 because they're not going to matter later on to the Lebesgue integral. Okay? So we define this type of convergence, which is weaker than saying that it converges pointwise, but will still allow us to recover a lot of the same results that we might otherwise expect because these sets are considered negligible. All right. The final thing we want to conclude with in this video is an alternate definition of measurability. Now, this is really a theorem. It's not a definition. And what I'm going to do is I'm going to show that this other statement is equivalent to saying that a function is measurable. So since it's an if and only if statement, you could really take it as its own definition of measurability. Okay. So we say that, so the theorem says a function f is measurable if and only if there is a sequence of simple functions converging to f almost everywhere. So again, one way to think about what this theorem is saying is measurable functions are almost simple functions, right? Since there has to be a sequence of simple functions converging to f almost everywhere, then I can sort of find a simple function as close to any measurable function as I would like. If you give me a measurable function, I can find a simple function that point-wise is as close to f as you would like. Now, we'll see sort of the importance of this theorem as we go on into Lebesgue integration. But this is just a really nice sort of alternate definition or alternate characterization of measurable functions. Now, I'm going to sketch out the proof here. The notation for this is sort of ugly, so I don't want to make it too bad. So what I want to do is I'm going to write out some of the details, but I'm also going to try to explain some of it simply by drawing pictures. So if we want to prove this, so let's start by supposing f is measurable. And I'm going to additionally assume that f is non-negative. Now, that's not an assumption in the theorem. It turns out that if f is not non-negative, then you can just split f into its positive parts and its negative parts and treat each of them in the same way that I'm going to treat just this non-negative piece. But for now, let me just assume that my function f is non-negative. And so what I want to do is the following. Now, again, I'm going to write some definitions here, and you're going to go like, what on earth are all these things? And then I'll draw a picture to help explain. So for each natural number n, I want to define a set A sub nk, and A sub nk is going to be the set of all x such that k minus 1 over 2 to the n is less than or equal to f of x is less than k over 2 to the n. And I'm going to do this for each k between 1 and n times 2 to the n. And then I'm also going to define A sub 0 n to be the interval AB minus the union k equals 1 up to n times 2 to the n of the A in k's. Now, I want to define, so now I'm going to define my sequence of functions. So this is going to be psi sub n of x is going to be equal to n times chi of A0 n of x plus the sum k equals 1 up to n times 2 to the n of k minus 1 over 2 to the n times chi of a in k of x. Now, I recall distinctly the first time I saw this characterization written out, and I went, what on earth? What are all these symbols trying to tell me, right? It was in no way clear, right, what all of these things were saying. It turns out, so we're trying to define this sequence of simple functions that are going to converge to f, okay? The idea is the following. I have a function f. So I have some function f, and it's defined on an interval ab, okay? And so maybe my function f looks like this. Okay, and maybe, so like here's a, and maybe here's b. Now, the idea here is take your domain, and what you want to do is you want to partition it up between, sorry, take your range, and you're going to take your range from 0 to n. Okay. Now, everything that happens to be, let me actually move this n down just a little bit, actually, for the sake of to illustrate this. So maybe I'll move my n down here a little bit. All right. Now, everything that is above n, let me get it. Okay. Everything that is above n, right, just gets flattened out. Sorry, gets flattened out to the height n. Okay. Everything, so between 0 and n, what you do is you break this up. So 1, 2, 3, all the way up to n. And you break each of these intervals up into 2n pieces. Okay. So you get a whole bunch of these little subdivisions in between. All right. What this is saying is, okay, this set A0n, that is all the pieces of your domain where your function value is above n. Okay. It's a little hard to see that from the definition, but if you look at these A sub n k's, the largest k value is n times 2 to the n. So if you plug in n times 2 to the n here, this shows you that the A sub n sub k's cover your function all the way up to n times 2 to the n over 2 to the n, which is just n. So everything else is in this A0n. And so what your function does is if your x value is in this set A0n, then it's just going to give you back n. Okay. Everything below this, what you do is you look at which one of these little subintervals you're in, and you actually round it down. So, for example, if I come here, I partition this up into a bunch of pieces. I look at all the function values that are between these two pieces, but I just round them down here. Okay. And then here, and then here, and here, here, and however many ways I've partitioned it up. Okay. So what this is doing is this is defining subsets of your domain where your outputs are in these particular partitions of the range. And so what you do is you start by saying, okay, in the first, when n is 1, you just take your domain from 0 to 1, you break it up into two pieces. So you just have 0, 1/2, and 1. Everywhere your function is above 1, which would be everywhere in this case, right? You just round down to 1, and then on each subinterval of the partition, you just round things down. So here you just get the constant function 1. Then you go up to 2, but now you break each part into quarters, okay? And you repeat this process, okay? Now, the idea of the proof, once you set all this up, and again, you have to play around with it a bit to understand exactly the mechanics here, what you can show is you can show that in defining them this way, for any fixed x, right, phi sub n of x is an increasing sequence. Okay. Furthermore, you show that if f of x is between 0 and n, then the furthest away that psi sub n could be from f is 1 over 2 to the n. Okay. So at each point, this is increasing. It's actually this second piece you show that it has to be between 0 and n, it has to be increasing towards f of x. Okay. And so finally from this, you can argue that the limit as n goes to infinity of psi sub n of x must be equal to f of x, but you have to be a little careful. This holds almost everywhere. Okay. So the reason this holds almost everywhere is you have to be a little careful about what's happening sort of at some of these break points, right? So it's possible that at these break points you aren't getting convergence. However, there are at most countably many of them. Okay? And so the set on which it doesn't converge are just these breakpoints, which has measure has measure 0. I was gonna say measure at most 0, but it's measure 0. Right? So this is sort of the idea of the proof. You build these approximating simple functions, right? And then you show that those simple functions actually do converge almost everywhere to f of x. So that concludes our discussion for this video. And with these properties of measurable functions at hand, we are now ready to define the Lebesgue integral. Now, given how much time we've spent sort of talking about simple functions and now having characterized measurable functions in terms of sequences of simple functions, it won't come as a surprise that what we will actually first do is define the Lebesgue integral for a simple function. Indeed, if you go back to the last video, we actually noticed when we defined simple functions, right, that in some ways there was a natural way to extend the notion of the Riemann integral for step functions, right, to some idea of maybe what the Lebesgue integral of a simple function ought to be. So we will, beginning in the next video, we will look at those properties again, and we will formally define the Lebesgue integral of a simple function, eventually working towards understanding how we can define the Lebesgue integral of any function, any measurable function.